Hey, nice to see you. Thanks for attending my talk. As it was mentioned, my name is Sebastian. I'm going to talk about scaling RabbitMQ at SoundCloud. And I'm going to tell you a little bit about what SoundCloud is. I don't know, who of you has heard of SoundCloud? Wow, that's a lot of you. That's amazing. So you're part of this figure. For those that have no clue, SoundCloud is an audio platform. A few numbers about our scale, our reach, is that so every minute we receive about 12 hours of audio that is being uploaded to SoundCloud. So 12 hours per minute is the current upload metric, and we reach about 200 million people a month, which breaks down to 8% of the entire internet, I've been told. If you know SoundCloud, you probably know these things. This is how we make the content available. So we're entirely user-generated content, and we offer a plethora of ways that this content is accessible. So there's players on the web, there's embeddable widgets, there's native applications for iOS and Android, and there's more things coming. Like I mentioned, all of our content is user-generated. So without our users uploading audio to the platform, we would not have any content. All of this user-generated content needs to be processed. So there's obviously audio processing for aspects of our various streaming formats. We support a wide range of clients, and basically the contract is that our platform is able to supply the required audio formats. So one of those is MP3. So as a SoundCloud client, as an official client, you're going to be able to access the audio streams encoded in MP3. Other aspects of processing the user-generated content is image generation. So all of these nice waveform images, they're all pre-computed. So upon upload, these things are generated and they're stored. And then when the content is delivered, we just basically read the processed content that we generated ourselves. We started doing this a few years ago in the advent of cloud computing and cloud storage. And the way it breaks down is that we store all of our media in S3, and we scale our processing of these assets in EC2. And a few years back, we had the big question of, okay, so we have this infinitely scalable storage, we have this infinitely scalable processing resource. How do we coordinate processing and storage and user uploads? And we picked AMQP as we evaluated a lot of different things. We looked at Stomp, we looked at a huge variety of freely open source, freely available open source projects, and we eventually decided to stick with AMQP. I'm going to briefly, who has heard of AMQP? Okay, that's also a fair amount, so I'm not going to be telling you any news. To those that have no clue about AMQP, AMQP has a very basic handful of useful primitives. So there's messages, which means they transport information, they encapsulate state, and they are delivered from A to B. Messages typically are delivered to exchanges or published to exchanges, which you can, the mental model is that's the mailbox at the post office, where you put your message in there, and then the post is going to take care of delivering it to the recipient. In order to know who the recipient is, each message has metadata, specifically a routing key, which is basically the recipient address. And then as soon as a message has been accepted, by the broker system, and the routing information is clear, it is routed to a queue, which is your local mailbox. So whatever message has been published with you as the intended recipient, it's going to be picked up for you from a queue, which is like your local mailbox at home. Simple diagram, so producer publishes to exchange, message gets routed to queue, and consumer reads from queue. Very, very straightforward. The key benefit of this queuing model is that the two actors in this system, so producers and consumers, are entirely decoupled. So by sticking a queue in the middle, you're making sure that, you know, if you ever need to scale, for example, your consumer pool, you can do that by just adding more consumers, and it's not gonna affect producers in any way. This means it's highly scalable. The part of SoundCloud that handles the processing of the user-generated content and the media assets is what we call transcoding internally. Transcoding just means input format, output format. It's not a great term because there's a ton of things going on nowadays. It's not just media transcoding, but that's still the name of that project. And the few of you that can read the slide, there's the R word, Rails. SoundCloud is a Ruby shop, or was a Ruby shop. The main application, everything that every single HTTP request that goes through SoundCloud these days is still terminated by the Ruby application, by the Rails application. We're working really hard on making that not so. So we're trying to, we're evolving our architecture towards a service-oriented architecture, and it's in some parts unfortunate that we have the history with the Ruby runtime that we have, because we have a lot of code in Ruby, and it all needs to be ported because you can't just say, okay, we're now service-oriented without redoing crazy bits of work that you've already done. So I'm going to walk you through, this is some Ruby code. For people that are unfamiliar with Ruby, it's fairly straightforward to understand, I think. And this basically is going to be a walkthrough of the high-level parts of the Ruby code base that are concerned with transcoding. So whenever a user uploads a media file, we create a transcoding model, which active record base signifies that it's something that is written to a database. We're using MySQL exclusively, for better or for worse. And the thing that is going to happen whenever this domain model of a transcoding has been created, we publish a message to the media exchange with the routing key, hey, media was uploaded, and the message is going to contain a unique identifier that we can later use to reference the asset that was uploaded. We're now leaving the Rails application, and we're hopping onto EC2, where something that we call the transcoder is running, which it declares a subscription on the media exchange, binds the media uploaded queue, and basically is the recipient of the messages that the Rails application publishes. So whenever a new message comes in, it's going to be dispatched to this do end block. There's going to be headers, and there's going to be the message. The message is going to be processed, and then the message is going to be acknowledged. There's more stuff. So when the transcoder has finished processing, like this is the high-level implementation of the process message. So do some work is all of the secret sauce that we're doing to transcode audio. When the audio has been transcoded and the assets have been processed, we publish another message saying, okay, media exchange, media.finished, containing the UID and the asset location. So this is the main responsibility of the transcode worker, is to perform the transcoding work and generate a variety of artifacts from images to media files and put them somewhere on EC2, on S3, sorry, where they can be addressed via URI. And then that URI is published, those locations are published and received by the Rails application, which then persists those in the database as well. We chose RabbitMQ as our broker implementation. It runs on Erlang, as most of you know. Erlang has this nice property, or the Erlang VM has this nice property of being rock stable. So we never were really forced to look into what is going on. We just added this component and had great performance, great operations, no issues basically. And we also didn't have any Erlang knowledge in-house. So it was introduced as a black box, and it remained a black box for a while. A simple diagram of how this looks. Our data center, where our physical machines are located, is in Amsterdam. RabbitMQ runs in our data center, and transcoding workers in AWS connect to the broker for coordination. And this is the first big scaling challenge that SoundCloud mastered, and we mastered this extremely well. So we have an auto-scaling worker pool, which means we can basically handle arbitrary amounts of user uploads. We can quickly and automatically scale the transcoder pool. So whenever there's a spike in upload volume, we're just adding more workers and in parallel process the workload. We learned that RabbitMQ is a really solid broker implementation that handles a lot of concurrent connections, a lot of throughput without too many problems. Here's an example of spikes in upload volume. So this is the queue depth of the media transcode queue plotted over time. This is a few days. And periodically there's going to be, I'm not going to say that those spikes are necessarily due to increased volume and uploads. There may also be issues going on, like connectivity issues to EC2 are a big problem. But anyway, so the pattern that you can see here is that whenever we spike and have a lot of transcoding jobs queued, the AWS autoscaler is going to kick in, and the backlog is going to be gone very, very quickly. So we've recovered from backlogs of many tens of thousands of uploads in a matter of a few hours, which is pretty good. So in typical startup fashion, this ended up working really well. So we should be using more of it because it just works so well. There's nothing that could possibly go wrong. So we started mapping more functionality onto RabbitMQ. The first thing that we did is, the Ruby runtime has a few limitations that may seem strange to people that are mostly doing Erlang. But the Ruby runtime basically has no concurrency. So every single web application server that we run can handle one request at a time, and that's it. So if we want to handle 200 requests concurrently, we're going to have to run 200 application servers. And we are running, I think, 500 these days. Yeah. So in order to sidestep some of these limitations and defer processing of expensive tasks, we introduced queuing of slow actions that would then be handled by a dedicated worker pool that only did one thing. And this would allow us to, satisfy an HTTP request very quickly, and then, do the actual work later. We also started building a lot of transcoding-like services, so things that work on the asset in S3. Among those are some really fancy projects that are way over my head, like auto-classification, auto-tagging, and content identification. So, we're basically applying machine learning ideas to the user-generated content to be able to say, okay, this is going to be heavy metal music, this is going to be dubstep. The heuristic in this case is really simple because 50% of the time it's going to be dubstep. So this is one of the hairier parts. So when we started doing this, we had one broker machine. So I don't usually do any testing, but when I do testing, I do it in production. And this is kind of what we did. We have this idea of namespacing exchanges and queues, and what we ended up with is testing and development queues on the production broker, which don't ever think about doing it. We've had so many issues of like even strange issues of people running code on their local machine connected to the VPN, and then just shutting the laptop at the end of the day and going home, and bindings sticking around, so queues would end up pooling messages, and there would be no consumers for code that was being tested. So eventually the broker runs out of memory, and the Erlang VM, as solid as it is, if you keep allocating more memory, at some point it's going to stop, and it's going to stop the world. The biggest scaling issue, RabbitMQ-wise, that we faced is a project that we internally call activities, and what it is feeds of site activity that are materialized for every single user. So if you sign up to SoundCloud, you're going to have storage in Cassandra allocated specifically for your dashboard. This is an example of a dashboard. So you log into SoundCloud, you see what happened since the last time you came by. It's very similar to something like the Facebook activity feed. We have new uploads from people that you follow. We have reposts from people that you follow, etc. The way we made this work is that we basically needed a mechanism to observe changes in the Rails application, figure out the relevant dashboards to write to, and then actually perform the write. So a little more Ruby code because it's fun. Ruby is such a quirky, magical language. We came up with a very simple idea of basically externalizing or advertising state transitions in the Ruby code base. So the title or the working name of this project is called Model Broadcast, and what it is a few lines of code that you include into your domain model, and then whenever our ORM would perform an action that would mutate the database, this mutation would have as a side effect a publication of the state, the new state in the database. This has a few issues, and this is why these issues are the reason why this is a scalability nightmare. So imagine there's a hugely popular SoundCloud user with 10 million followers, and that person uploads a new track to SoundCloud. So the first line of code or along those lines would be executed. There would be a message published to the model broadcast exchanges. The consumer would select perform a select statement against the MySQL database to figure out, who should I notify of this upload, and then it would publish one message for every single dashboard that would have to be updated. So in this case, we're turning one trigger message into 10 million event messages that need to, eventually also turn into Cassandra writes. So Cassandra is handling a lot of writes. That's crazy. And we basically ended up in a situation where, we had a single point of failure in our architecture, and we were heavily depending on it. There was no fault isolation. There was no resource isolation. So whenever, Skrillex would upload a new album of 10 tracks, and all of his 10 million followers would have to be notified, that would be 100 million messages that would just be pushed through all the systems and then ripple through the infrastructure with it sometimes not holding up. And this, up until maybe a year ago, this was the daily reality almost. At some point during the day when traffic was high, there was a lot of site activity. The broker would start to stutter, start to apply back pressure on producers who, by virtue of their not optimal AMQP client implementations, would just buckle and crash. So the broker would die and the site was down. Yeah, it didn't help that SoundCloud is we have an interesting popularity distribution, I would say, where we're mainly known in Europe, but if the US wakes up, our wires start to glow because it overlaps, US waking up and Europe, early afternoon, late afternoon. This would mean that would be our peak time. And we would have incredibly bursty loads that we would just not be able to handle. So every once in a while, things would just fall over. Here's a fun graph. I hope you never see something like this. This is memory allocation for one of the problematic brokers. And what you can see is that it just increases every single time, and then every one of those drops, that's a machine restart. So that correlates to uptime, and I mean it's impressive uptime. It's like a few months at a time, and then it would be dead. So I mean this is a little more than a year in total. So, but still, this is not optimal. It's very impressive that it worked as well, but you don't want to be in this position. So of course, what did we do? We had some funding. We were able to buy additional machines. So what we did in our capacity planning is we said, okay, we're going to buy another broker machine, and we're going to partition the workload. So have the old broker handle site traffic and transcoding, and handle the new broker have the new broker handle activity feeds. We started using more queues because we were gaining knowledge about how things work internally. So more processes, aka more queues, means things work a little smoother. And we had some breathing room. But not for long, because we still had single brokers, no higher availability. So whenever there was issues, and there were a lot of issues due to our traffic pattern, we would still be down. So eventually, we discovered, okay, this cannot go on like this. We need to come up with a scheme of higher availability, and if that is going to end up being something that scales, that's great too. So what we did is really simple. We introduced, instead of having physical machines be the broker, we said, okay, we're going to have multiple machines form a cluster, and this is going to be one logical unit. And as an application, your configuration would always point at one of these clusters. You would publish to one, and you would subscribe from all brokers in that cluster. A little diagram to explain this a little more. We would have a very straightforward setup of putting a load balancer in front of a RabbitMQ cluster. So the load balancer would be something like IPVS. And what it would do is when a worker process would want to establish a connection for publishing messages, it would connect to the load balancer. And if it wanted to consume messages that have been published to this topology, it would establish direct connections to all of the backends. And this has the benefit of when one of the backends goes down, you're still in a position where you're able to maintain service. There was only really a few changes that we had to force upon our clients. So the big change is, instead of having one connection to one broker that you would use to publish messages and consume messages, you would be connecting to one load balanced broker for publishing, and you would connect to n backends for consumption. Whenever one of these TCP connections would go away, it was upon you to reconnect periodically. So with some backoff algorithm, the onus would be on you to reconnect to the faulty machine. We also discovered that using AMQP heartbeats would make this a little smoother, because in the case of a client crashing, the broker would know faster that the client had gone away. We've had some really weird experiences with consumers being listed as active that had crashed a week ago. This is the activities broker topology. It's currently two machines, and this is a plot of the publish rate over time. So you can see our diurnal rhythm. So every peak would be afternoon of a day. This is a weekend. Also interesting, maybe. And you can see that we're handling on average at peak time something between 20K and 30K messages a second. Those are all persistent messages. And I drew a little arrow into this plot, because we actually took down one of the machines at that time and performed maintenance. We did a kernel update because there was a Linux kernel vulnerability, and operations people told us to upgrade. So this is actually full-on operation with a maintenance window, and there's no impact on throughput. So the benefits of this approach, it's really simple. All logic is in clients. We have achieved availability, something that was the motivating factor for investigating these options. But we've also discovered that we've kind of by accident added scalability. So by virtue of publishing connections being round-robined over all existing backends, if at some point one of the backends is at the limit when it comes to publication rates, we can just add another backend and have messages or message volume be allocated by a third per backend instead of half and half. We've actually pulled this off on a variety of platforms. SoundCloud is a very polyglot company these days. So obviously there's Ruby, there's the JVM clients, so Clojure and Scala are things that we use heavily. I'm personally proud that this is in here because that's all me. And we have a big momentum of Go right now. So there's a lot of, we've actually developed an AMQP client in-house that is available for the Go programming language. There's going to be a lot more work, of course. I mean, we're in a position where we have breathing room. We have solved our immediate issues. We're available. We're scalable. But you know, the work never stops. So the position that we're in right now is that we're running basically 2 clusters, one for the activity feeds and one for everything else, which is obviously a bad idea when it comes to fault isolation. So, you know, if the activities topology, you know, should have catastrophic failure and would be down, that's fine. But if the other topology would go down, there would be so many services that are affected that it's not funny. So we need to, you know, instead of, one of the things we did is, you know, more funding, bigger hardware. We did not make the mistake of, you know, skimping on the broker machine upgrades again. So we actually have super beefy machines with 24 gig of RAM and many cores running our RabbitMQ brokers right now. But that's not how you want to scale these critical components. So instead of having really beefy hardware, we want to use commodity hardware. So in our case, that would be what we consider application class machines. So, you know, just not as much RAM, not as much CPU. The other big thing is that, you know, with we still have some artifacts of the exchange and queue name spacing around. So there's still, like, every single queue is still called production live something, and that is just, you know, a relict of how we started doing this stuff. And using, you know, active record side effects as your integration API is a terrible idea as well. So we actually want to, or what we are doing right now is we're moving towards an API that is much stricter, much more well-defined than, you know, arbitrary MySQL column names, which has the working title semantic events, and this is actually going to be a very key component in our service orientation efforts. So we're going to be using the semantic event system to advertise state changes in all of our applications and use AMQP as something of an overlay network to, you know, shuffle state from things that are in charge of that state to things that are interested in changes of that state but are not in charge. The big thing that we're working on in parallel is discovery. So right now what we're doing is we're manually assigning physical host names to applications. So we're saying this is your broker pair, connect to those 3 brokers. And in the future we want to have this a little more dynamic. So we want to be able to, you know, when our configuration management brings up a broker instance, we want it to register in a central registry, and we want applications to, you know, switch over to new resources when that is necessary. So instead of, you know, hard coding configuration values, we want to have configuration dynamic. And that's it. Any questions? Yes.
I'm surprised that you push all these details of your broker configuration into the clients.
Yeah.
So, like, just wondering, like, maybe you want to build some kind of service
Mm-hmm.
and let the clients consume,
Mm-hmm.
like, publish and consume messages from the service, and basically factor out all of that.
Right. So abstract AMQP.
In a sense, yeah.
We thought about it, and it's actually something that is in the back of my head for, you know, things where we're currently seeing problems with AMQP as a transport. So, things that run in a physical location that is far away from our data center, we have historically had issues with long-lived connections, which is AMQP, a TCP connection that tunnels AMQP is a long-lived connection. So we would occasionally see those connections go away, and some abstraction that would do maybe TCP keep alive or HTTP keep alive, but much shorter connection times is something that we thought about. We haven't fully done it, and the service discovery component is actually going to be something like you only, like as an application, you only have to advertise this is my name, like this is my application name, and the response is going to be, okay, here's your broker configuration, and that can be one broker, that can be 5, that can be 10. That is entirely not up to the application to decide. That's currently how it is because we don't have the discovery mechanism, but we're working on it. Yeah.
What do you plan to use as the underlying storage of the discovery data?
Yeah. So there's so we have a prototype, and it's not going to survive prototype stage. I'm going to go out on a limb. There's a few, like I mentioned, Go has a lot of momentum at the company right now, and there's a Paxos implementation in Go, doozerd, which currently functions as the storage, as the distributed storage of the discovery state. doozerd has this unfortunate history of, it was built by Heroku, and it was then abandoned. So, it has some issues, and we haven't solved those issues. So we're probably gonna investigate other things. Yeah.
If you have a disk failure on one of your brokers,
Yeah.
other jobs that are going to be never complete.
Yeah. So one of the big drawbacks of this system is that if you have this cluster and you're not using RabbitMQ specifics like mirrored queues, in the case of a catastrophic failure, so that is something where you lose storage, so your hard disk is not recoverable. We're going to be losing messages in that case. And the other thing is, even in a regular outage, like a maintenance outage, what is going to happen when the broker comes back up? There's going to be messages stored on there that are going to be way out of order in terms of temporality. So we're not losing those messages, but they're going to be arriving 2 days or however long the maintenance takes after the fact. And that is actually something that's very, very easy to combat or to minimize at least, which is your queues should be empty. And they should be empty anyways, because otherwise you have problems. Yeah.
Did you consider Apache Kafka?
We did. We actually looked at a lot of things, and one of the, I mean, it's stupid, but it's always this periodical thing of what is technology that you want to invest in and what isn't, and the JVM is one of the things that a few years ago deterred everyone from I don't want to be on the JVM. I'm going to use everything else, and this is now changing. A lot of people that know way more about distributed systems and work queues than me have looked at Kafka, and we have decided that we're going to stick to RabbitMQ. Yeah.
What do you use Closure for at SoundCloud?
That's actually the organization of SoundCloud engineering is application teams. So what used to be the monolithic Rails application is now actually 4-5 teams that are re-implementing bits of that functionality, and most of our new web application layer is written in Closure. All right, thank you.